Okay, so of course, all of you can zoom on the main screen so that you can see the slides clearly. So I'm going to start now. Thank you to the organizers, Julia and of course, Daria, for inviting me today. Thank you all for being here. Today I'm going to talk about continual learning for production systems. Again, I was saying that I'm a president co-director of research of ContinualAI, which is a nonprofit research organization working on the same topic, continual learning. I'm also the teaching assistant for the courses of machine learning computer architectures at the University of Bologna, the Department of Computer Science and Engineering. And I'm also one of the co-founder, board member of an organization, AI for People, which is all about trying to develop AI systems that are sustainable and respect human values, and that we can apply AI technologies for the good of humanity. Of course, if you're interested in the topics I'm today about continual learning, please check out our organization, ContinualAI, on our official website, continualai.org. ContinualAI is a nonprofit organization and largest open community on continual learning for AI. And now it counts more than 800 members in 19 different time zones from all over the world, top-notch research institutions, as well as companies. So if you want to learn more about this exciting topic, just all right, so all the algorithms and experiments I'm going to present today are, the results of a fruitful collaboration at the University of Bologna within the Machine Intelligence Biolab laboratory. She is supervised by my supervisor, Davide Maltoni, and it's a work made with other two brilliant PhD students, Lorenzo Pellegrini and so in this talk, I'm going to follow this outline. I'm going to start with an introduction and motivation on why I think continual learning is very, very important for the future of machine learning, especially into production environment. And it has some, similarities with the Agile methodology when developing software. And then we're going to try to define a bit better what continual learning is and why it is useful in this case. Then we will move to the most technical part, I would say, of this talk, trying to introduce AR1 star, which is an algorithm, a continual learning algorithm we proposed recently. It is an efficient strategy that was made specifically for real-time continual learning with high-dimensional streaming data. Then we will close this talk with a use case about real-world deployment of this strategy in a continual object recognition application on a use Android device, very low-ended device with no GPUs. We learn on the fly on this. All right, so let's dive in. So as scientists, but maybe most of all software developers, since the 70s and the 80s, we have learned how to start from some requirements given by a client, and then to produce a software that could satisfy these requirements. And the main approach during these days were based on what it was called the waterfall model. It is a linear development strategy for starting for the requirements and up with a software can work to satisfy these requirements. But it was proved somehow to be unable to work in a, let's say, in a very complex and fast-changing world as it is today. So from around 2010, the Agile and Scrum methodologies became the standard de facto for development these days. And essentially, they were based on these four, let's say, key properties they would enable. So adaptive planning, evolutionary development, early delivery, and continual improvement. So the idea that you cannot have a perfect software, you will never have a perfect software, But you have to acknowledge the fact that the world is changing, the requirements are changing. You need to integrate new features on the fly, and you never, stop working on a specific project or software project that is going to work within a product or a service. Properties enable you to develop these software iteratively, rapid and flexible way, so that you can respond, very fast to changes in the requirements. Client is constantly, asking you to, and this was proven to be very effective and important. So maybe some of you in the audience, you can ask at this point, why are you saying this? What's the relation with machine learning? Well, let's start from a blog post from 2017 from Andrei Karpathy, which is, as you may recognize, the director of AI at Tesla. He was foreseeing this blog post a fundamental shift in the software development world. Okay, we can read these quotes directly from his blog post. So he says, I sometimes see people refer to neural networks as just another tool in your machine learning toolbox. They have some pros and cons, they work here and there, and sometimes you can use them to win Kaggle competition. Fortunately, this interpretation completely misses the forest for the trees. Neural networks are not just another classifier. They represent the beginning of a fundamental shift in how we write software. They are software 2.0. So the idea that he's trying to convey here, Karpathy, in 2000, that maybe we are moving in another direction for software development. Sense that we are using, instead of our minds, we are using automatic optimization, machine learning optimization algorithm to design and create our software. In the end, in this case, is our predictive model. So the way we are doing software maybe is changing, and we're seeing these more and more nowadays. Every possible pipelines in environments for every product and service, we are now changing many different modules and submodules with end-to-end predictive modules that are somehow trained directly from the data without any handcrafting, from humans. They are completely automatic, and in the sense they are creating software by their own. So the problem is that with current machine learning models and algorithms, current machine learning algorithms are training models in an efficient way because they are trained from scratch and simply deployed at every iteration cycle, making them somehow similar to the pure sequential waterfall model we have seen used in the past for software 1.0. So very rigid and difficult to adapt. So in essence, the parallelism I'm trying to draw here is based on the assumption that data are now the new software requirements, coming and changing through time, and train a refined model to produce, to respect the changes in this data. Then the second point here is that the training process is the actual design and development phase, resulting in the software product, our prediction function, our prediction module. So how can we translate what we are learning in the last 50 years of development in to software 2.0? So how can we think at a development phase, that is a training process in machine learning, can be changed on the fly when the data that are coming to our changing? So how we can somehow simulate the agile, iterative, and efficient development cycles with machine learning? And the answer to us is to use continual learning. Continual learning essentially is a particular subfield of machine learning that is so concerned about this idea of training mentally, continuously, from ever-changing data distribution. So essentially, what we would like to do is to move away from this very rigid separation between training offline and then deploying the model with frozen learning capabilities, and move towards a more smooth and natural way of learning, where we constantly update our biased understanding about the external world, always improving and generalizing through time with a single model. So practically speaking, as we encounter a couple of distributions, x1 and y1, and we would like to learn a mapping function, our neural network f of theta from the x1 to the y distribution, then as we encounter another couple of distributions, x2 and y2, what we would like to do is to generalize our prediction model f of theta to handle both mappings, but without accessing anymore the data belonging to the x1 and y1 distribution. So essentially what we are saying is that we want a single model that is incrementally trained, but without accessing the data that we encountered before. This process is what we define as continual learning. So continual learning enables three important, or critically important problems, properties that we would endow our systems with. So efficiency, adaptiveness, and scalability. So first of all, as the process is continuous, we don't need to start from scratch every time, relearning the things we have already learned. Of course, this can enable a very fast and efficient and flexible way of learning, guarantee adaptation and customization capabilities at an unprecedented speed, because we don't have, again, to retrain everything from scratch. And then another super important point is the scalability property. That is, we can have somehow computational and memory overheads that are bounded, very small, with respect to the standard, let's say, retrain and redeploy strategy. And these would allow us to scale in terms of intelligence by processing more and more data, because again, we don't need to store the data. We have just to filter the external, let's say, reality, so that we learn from it and we compress the knowledge about it in a model. But we don't have to somehow store all the data, so we have to add new resources, new memory resources over time, and we don't need to somehow support increasingly overload in terms of computation, because we don't need to retrain everything. So as you may imagine, continual learning may enable tons of different applications. But what I want to emphasize here is it's not just a matter of developments and in the remote future. I think that continual learning may benefit a lot of today's applications. For example, embedded systems and robotics. In this case, for example, privacy is a major constraint, and continual learning, you can avoid to store data on these devices. You can learn very fast and efficiently on the edge, and you don't need a cloud infrastructure or an internet connection. So data, and you can work directly on data on the fly. Then a second possible scenario application, I think it would be very useful today, is AutoML and continuous integration systems for AI models. So every service out there now is starting to have an AutoML and to essentially update the prediction models based on the customer's data. And in this case, continual learning would enable, again, scalability, efficiency, and fast adaptation, but most of all would spare a lot of energy, and in the end, cut your AWS bill by a lot. And finally, another application I'd like to mention is bias removal. So in this case, continual learning can see a question. Maybe I can ask that. It was in the past. See what so now the slides, the current slide should be practical applications. I hope you are aligned.
So,
are you seeing a practical application slide, the number 10?
Not yet.
Okay. Maybe I'm too fast for very data.
Click it again.
Okay, let's try to.
So, please, everyone, Write or tell what I've seen. Utility, plasticity, dilemma.
Okay, now it should be practical applications.
Practical applications, I see. Yes, yes, yes. A lot of people see the same.
Now we are aligned, hopefully. Okay, great. So again, yeah, I was saying, yeah, bias removal may be a very interesting application when you want to use continual learning to update your bias system or a system, a predictive model that has a flow, a security flow. So in that case, you can, as you would do in your normal software 1.0, you would add a patch to that system, and you could do the same with continual learning. You can just find a few data from which to learn from that can, close this fallacy or, remove some bias in the data and then apply that patch to your system. And that's another application of continual learning. Okay, but so the question here is now, why aren't we using continual learning today then? So interesting and useful. Well, I think there are two different explanations for this. So the first one is that every company out there is willing to spend a bit more, but somehow keeping control of the data of its users in the sense that they want to store them, they don't want to erase it, they want to store every data as possible because you may find another interesting use of the data later on. And the other important aspect that we have to consider here is that there's what is known in literature as to be the stability plasticity dilemma. So the fact that it's very difficult to learn continually and to find a trade-off between remember past concepts that we have learned before and learn new concepts and generalize over time. So that's very difficult to do also for biologically learning systems and for artificial systems as well. I mean, it's also very reasonable to get that it's easier to learn when you have all the data in advance, right? You can have them all in front of your eyes, and you can find the best solution to the problem. It's much more difficult to find new evidence over time and to try to come up with analyze for all the things we have seen so far. But for gradient-based deep architectures, especially neural networks, problem is even worse in a sense because we are subject to what is called catastrophic forgetting. Is as soon, if you're, for example, training a neural network with gradient descent, as soon as we encounter a new piece of data, we completely erase the information we have encoded in the weights, in the parameters of this network to suit only the new data distribution, called catastrophic forgetting or catastrophic interference. So in the last few years, we have seen a number of proposals, algorithmic proposals, to try to address this problem to tame catastrophic forgetting in neural networks. I would say from 2006 especially, and now there's a lot of interest from the deep learning community topic. And in this light, I summarize some of the strategies that have been proposed. We're not going to go into details for each of those, but I wanted to just give you a quick outlook of the main categories of approaches you can find out there. So the first one is the regularization approaches. In this category, find all the strategies that are somehow based on the idea of regularizing learning on the new piece of data that you may have, trying to preserve the weights that are important for the previous data distribution through a regularization term that is added to the loss function. Okay, so now the slide should be the 18. So continual learning approaches.
Sorry, Vincenzo, again, the same quest about refreshing the slides.
Yes.
Still 16.
I try to refresh the page, so now it should be 18. So continual learning approaches. See? Very strange.
Audience tell or say anyone? Yes, they still see.
Yeah. Try to go back and forth.
Everyone, and me too. Oh, now it's number 18. Yeah.
Okay.
Who also see 18 slide? Please tell us. Yeah. Okay. Good.
Okay, great.
Sorry.
Just tell me when you don't, or maybe when I switch a slide, I say every time that I'm switching that I'm doing so.
Yes, it is a very good idea.
Yeah. Okay. Cool. So I was saying there's a regularization category, then there is the rehearsal one, in which what we do is to allow essentially ourselves to maintain an external memory of fixed sites in which we can store data, raw input data from the previous, and we use this external memory to rearch from it so that we don't forget, let's say. Then there is the generative replay category, in which these strategies, what they do is to, instead of storing an external memory, they have a generative model. They try to learn on the fly generative model that can regenerate input data from the previous data distributions from which to from. And then the architectural category, in which strategy essentially is all concerned about changing the architecture of the model. So maybe freezing parameters, adding some others, isolating other parameters, so that you can tame the problem of catastrophic forecasting. And of course, for all the information I'm talking about in this talk, you can find the bottom of the slide, the paper from which I'm taking this content or discussing some. Okay, now I'm moving to slide 19. Essentially, this is the most technical part of the talk. So we are going to quickly have a look at what can be a continual learning strategy. So in this case, it's Air1 Star, which is a strategy we proposed recently, and it's an efficient strategy for real-time continual learning on also low-ended devices, as we see. And it's very competitive with the rest of the strategy, especially with when addressing high-dimensional streaming. So I'm now switched to slide 20, and essentially for the experiments I'm going to show you here, we are going to consider the following scenarios. So, okay, now I'm in the next slide, in slide 20. Okay, great. In this scenario, what we have is, let's say that we are in a classification problem. We are trying to solve a classification problem. And for simplicity, let's consider an object recognition classification. So we start with an initial batch of data, batch 0. And in this batch of data, we have a number of examples of different classes, right? Then what we do in our continual learning setting here is to encounter a number of incremental batches. And in these batches, each of these batches can have inside new examples of the same classes you have encountered in batch 0, or they can have examples of new classes you have never seen before, or as a third option, you are agnostic essentially to the content of this batch. Find new examples of classes you already seen before, as well as other examples of classes you never seen before. That's the best scenario in which we are gonna propose our AR1 star strategy, which is we think the most natural one for a robot, for example, interacting with its environment. All right, so we're now moving to slide 21, and in this slide, I summarize what we proposed in 2017 as a new benchmark for continual learning and object recognition, following exactly the scenario I was presenting in the previous slide. So Core 50 is I guess the first benchmark of specific learning, and the idea here was to provide a small enough but not so small, I mean, natural benchmark, video benchmark with a natural interaction with the environment. So slide 22. You can see, I hope here, I hope you can see here on slide 22 the videos for each of the 50 different objects contained in Core 50. There are 50 different objects of 10 different categories, and essentially we have taken 11 different sessions for each of those objects, video sessions, in a very different environmental condition. This is very interesting because you can really assess the ability then of a continual learning agent that is trying to improve the recognition capabilities on some classes when it encounters new different conditions for the same objects. Maybe they are degraded, maybe they are in some different lighting conditions, maybe they are encountering an outdoor scene, so a very different condition. So that you can generalize over time we recognize those objects. And the data set is manageable enough so that it counts just 164,000 images of mostly 128 image sites, and it's manageable enough so that you can prototype new learning strategies, but at the same time it's realistic so that you can bring these algorithms into the real world application. All right, so I'm now moving to slide 24, and in this slide you can see that we have defined four in this case, but even more. I mean, we have even more protocols on top of these data. But for this talk, I'm just gonna talk about these new instances and classes, NIC version 2. Two protocols. See if I update this slide. The slide 24, and in this slide I was saying that different protocols we define on top of Core 50. So essentially, these protocols are based. What they do is working in the scenario I was discussing before, but with a different number of incremental batches. So I don't know if you can see my mouse, but essentially you have the 69, 196, and 300 and 391 protocols that they are based on this number of batches. And of course, when we have more batches, the number of images contained in each batch is lower, and as well as the number of classes. So these protocols are essentially in an incremental complexity, because it's much more complex to have a long sequence of small tasks than a few number of batches that are very big. So the most difficult one here is the 391 version 2 protocol with 300 images, one class only for incremental batch, so that essentially we are just taking one video session of an object smoothly moving in front of the camera, and that's the only data that you have to update your model. So it's very, very complex to work on these non-ID small batches, being able to improve our recognition capabilities while being able to tame catastrophic forgetting. All right, so this slide 25, you should be able to see a neural network depicted here as a sort of a pyramid. Ready, but dated, fresh. I refreshed. It. What about now? Great. All right, so essentially our approach here one is based on this idea of somehow dividing the network in parts and applying a different continual learning strategy that is different for each of those parts, because they're different by their nature, so it's important to handle them differently. So there is the low-level generative features layers, there are the class-specific discriminative features layers, and then there's the output layer. So for the low-level generic features, what we do here is to start with a supervised or unsupervised pre-training from ImageNet, and slowly fine-tuning that, or you can keep it fixed as well, because as you may know, a training on net million images and 1,000 classes produces very good low-level generated features that you can use for every downstream tasks, computer vision task, and they're good for Code 50 as well. But then, I mean, we would like to move in future directions for this approach towards more unsupervised pre-training strategies from scratch, for training with respect to the upper part of the network. The upper part instead based on it's based on a regularization approach, continual learning approach. I hope you can see now slide 27. In this slide, essentially, I report the loss function definition with additional regularization term. And this was firstly proposed by Elastic Way Consolidation Strategy, by DeepMind, and other similar approaches. What we are doing here differently is that essentially we are computing the importance of each weight in a different way, in a more efficient way. So yeah, actually what you can see here with the L new is the loss function of the current batch, the batch. Actually, what we do is to add to the standard cross entropy loss function L new, we add this plus a regularization term followed by this lambda parameter, and essentially this summation is trying to disincentivate changes in the weights that were important for the previous data distribution. So this omega term here for the weight k, for each weight k, is describing the importance of the weight as essentially this, as we move away from the optimal parameter theta k bar with the current parameter theta k that we are changing over time. I mean, if the parameter is very important, this term is going to be very big and is going to impact on the whole loss term. Since we want to decrease the entire loss term, then this behavior is going to be. But we do that in an efficient way. I don't think I have time to go into that. You can look at the details at the paper. You can find it on the slide. But essentially, we do that in a way that is computationally efficient and independent from the number of training batches. So we have a fixed overhead in terms of computation and memory for handling the importance, let's say, of each weight, and to regularize the network so that we don't change so much the weights that are important for the. Then we also, in the same paper, we try to highlight the importance of batch renormalization, which is a variation of the normalization strategy often employed in partner network for regularizing the activations of the network. I hear a bit of noise from, I think, Andrew Angle. All right. Instead, the output layer is handled in a different way as well. So in this case, we try to work on a dual memory system with the idea that you want to have a memory that is very plastic, that it changes very fast to learn new concepts, and then consolidated memory. You want to store like long-term memories and concepts. And so this is exactly what we do. And with this approach, it's called CWR star. just for handling the output layer or the linear classifier of our network. And in this case, we are able to generalize to handle settings that was described before in our scenario in which we operate, so that depending if you have a new instances classes or new instances of classes, you can work on those settings as well. So I'm talking on top of the slides 29. Okay, maybe you are one. I refresh now. Be able to see slide 29. To slide 30. So I hope you got a feeling at least of what this strategy is doing. Now we are seeing the results in slide 30 of this approach. So it is solid red line, Air 1 star. And you can see that is somehow on these three protocols from the left to the right, here to the right, the flex on the right. You can see that the strategy is working very well with respect to the state-of-the-art reaction-free strategy. So all these strategies, they don't use an external memory. And but at the same time, you can see there's a huge gap back to the upper bound. That is this dashed line that essentially is representing an offline training on the world training set, one shot. So it's not a continual learning strategy, it's just the same model trained on the world training set of Core 50. And of course, it's much better. And essentially what we lose, especially in the protocol 391, we lose like more than 30% accuracy points. So again, you can see that the curves are growing over time, so that's nice. But at the same time, this is not very compelling for real world application or scenario in which, as a company, you would like to even spend more, but what's really important is the accuracy performance at the end. So you generally you are willing to spend more to get more accuracy on your problem. So there's a lot of space for improvements, I would say here. But the nice part, especially for this very simple approach here, 1 star, is that we have times 69 speed up with respect to the cumulative strategy, the strategy in which we retrain everything from scratch on the accumulated data. And every time we encounter a new piece of data, and we are 93 times more efficient in terms of memory, of course, because we don't have to store any data. So the nice thing again about Air 1 star with respect to other strategies that are being proposed in the literature is that it's very computational memory light. I mean, it's very light in terms of computational memory, and is fixed in terms of overheads. So it's not growing linearly with respect to the number of batches that are processed. Very nice because it can tackle an unlimited number of increments. But how can we close the accuracy gap? As I was saying, it's the one of the part. How much time do I have left, Julia or Daria?
So the time is almost over, but maybe some more additional minutes you have.
Okay, a few minutes. So a few minutes. I think that maybe we can skip these slides about the closing the gap, the accuracy gap, and essentially the trick here is to add a bit of replay, a bit of rehearsal, but not at the input raw input layer, say with raw input data, but with activation volumes. So you can, as you can see in slide 32, I hope you can see the slide. Essentially, you can extrapolate at some point in the network some activation volumes, store them in external memory. So it's very light in terms of memory overhead in this case, because we are not storing images. And then you can concatenate on the fly. It's still 32. Yeah, still 32. It's 32. It's cool. You can see that these volumes on the fly at the mini batch level while you're learning about new data from the current batch. That's very cool. It's very efficient. And I just show you here the table at the tables at slide 34. You can see here that we are just 5 percentage points away from the, say, rehearsal from scratch, which is of course more effective in terms of accuracy, but it's much more computationally and memory demanding. And with this strategy, if we say like we choose to do the replay from a latent space, which for this mobile net version 1 is ACOVNet 5-4, we are able to run the code on a single GPU in just under 2 minutes and with just 48 megabytes of memory overhead. And staying away from, from the cumulative upper bound of just 13 percentage points. So not 30, but 13. So a huge improvement. All right, so I think that I can show you directly the use case now, is just to close my talk. So essentially what we did was to try to see how this strategy, how this algorithm could work in a real world application. And you should be able to see slide 36 now. Essentially, the core Android application that we developed is based on Air 1 Star. Great. And this application is an object recognition application, which essentially let the users train the model directly on the edge on the smartphone, so without internet connection. And essentially, you have 10 different classes already pre-cablated in the model, and you can improve the recognition of one of those classes, so being able to recognize new objects that you want to recognize, or you can add completely new classes of objects. And I think, of course, again, this is working directly on CPUs, so without using any GPUs, and it takes training takes about 1 second on the environment, at least on the let's say an average Android phone. Okay, Julia and Daria, how can I play the video now? Should I play it?
I can play you. I can turn it on left screen.
Okay, left screen.
Better.
Okay, I can see it.
I will be glad if someone or every one of us will do right or say, do you see? Yeah.
I see the video that has already started on the left screen. I think I can comment it directly, so you can see the application which is running on the smartphone, and essentially now we are using it just in inference. So we are showing to the camera on the first screen. We're showing the object, the domestic object, and working here in inference. Well, it recognizes the object that we have already there. Now, see how it works in training. So, first of all, yes, the video started. Some of you are I don't hear you.
Wait, I'm stopping the video.
Yeah,
Yes,
right.
left screen.
Yeah.
Now.
Yeah, the music was nice. Yes, let's.
Yes, I can make the link up. Vincenzo, can you put the link in chat?
Yes, I'm trying to go, but I cannot.
Do that. Sam done?
Okay. Okay, let me know when I can play my video on YouTube so that we can be.
Probably everyone can watch this video separately on
Okay.
their laptop.
Okay.
And
So
also,
maybe
yeah, sorry, continue.
No, you can. I mean, the video is self-explainable as well. I mean, it has like caption inside it, so I think you can see it later and understand very well what he's doing. And of course, if you have any question and about the video, about the app, or about the specific approach we use, you can send me an email at Vincenzo.Lomonaco at unibo.it. Okay. So this was the end of my talk. So I am open to questions. Go ahead.
Yes, let's all together clap for Vincenzo. Thank you very much, Vincenzo.
You're welcome.
You can push button F4 to clap for our speaker. Yes. Thank you. So yes, and please ask a question. You can also raise your hand, pushing the button below in your screen. Button with a hand.
Yeah.
Ask a question or just unmute your mic.
There's a question from Nazar.
Yeah.
Okay.
So thank you a lot for presentation, a lot of useful information. And also I want to ask that could you share your presentation or paperwork name to find it or on archive.org?
Yes. Yeah. Of course. Almost every paper is published as well as a preprint on archive, so you can find these papers without paying anything. Of course, if you, I mean, I can also send it to you, but you would be able to find it directly on Google, just typing the title of the work. But of course, contact me if you. And the slides, yeah, the slides, I'm going to just, I mean, I already sent the slides to Julia, so I think that she can website, I don't know, whatever you prefer.
Okay, thank you.
You're welcome.
Everyone who has a question can also speak with Vincenzo after his speech here, or write him, and I will introduce you his contact.
Great. I think that Volody has a question as well.
Maybe Volodymyr has a question, but can
Okay.
speak.
You cannot.
Maybe he can.
You can write. Yeah, you can.
Yes, he is writing. So the question is already in our public chat. I can read it. Okay, first of all, really great topic and presentation. Thanks a lot. I was interested in the following question. What was the optimizer that you choose for training? And do you consider to further model optimization in terms of latency, size, and speed?
Nice question, thanks. So for many of our say application of the algorithm main benchmarks, we use the classic stochastic gradient optimizer without other so we use the plain SGD optimizer, and then we use eventually our recommendation strategies and terms. But I think there's a lot of space for research and improvements on top of that. I know for a fact that these optimizer, of course, impact on so for your application or the specific benchmark you're trying to tackle, you may want to check if different optimizers have different results and choose accordingly. But yeah, it's a safe bet to work with just then of course for the future we are trying to still work on the trade-off that is the core issue of continual learning between efficiency and accuracy. So efficiency means size of the model, size of external memory, size and the speed of the model as well. So yeah, of course we are interested in algorithms that can work by benchmarks, but as well in real life. So that's why we try to keep the time maybe below the hour or reasonable training times. Later work on real world application. Yeah, the extension of our work that we are trying to tackle now is to integrate in our R1 strategy a generative model to generate the activation of the volumes. I was very, very difficult to do because it's very difficult to train a generative model on these very small training batches. We are trying to work protocol based on 450.
Thank you, Vincenzo.
You're welcome.
Thank you, audience. Thank you very much.